Hey dudes, sorry I'm not here with you today. I'm hanging out with my daughter. She got some sort of weird virus and looks like she's been stung by bees. Not a happy camper. She got like hives all over her. So anyway, we're gonna hang out digitally. We're looking at the beginnings of logs. Some of you have already like started cruising through this. Cruise away. You know what you need to do. If you are new to logs or still like just a little not sure, oh there she is. Maybe you can hear her. That's all right. Jump in with me here, and we'll get it straightened out. So this is just sort of a warm up problem. We don't have to actually go through the whole thing, but um, we looked at growth, and they said here's 280 taxis, and we're increasing by 12%, 1.12 every n year, right? And you could find the number of taxis at the end of 2005 by just putting 5, right? This was the year 2000, so in the year 2005, we would put 5 in for n, and you'd solve for t, no problem. But if you said, all right, find the year in which the number of taxis is double the number of taxis at the end of 2000, we would be inputting something into t and looking for n, right? So double the number, I don't know what it is, so you'd say, I have a number for t, I don't know where our number is. This is 280, and I don't know, let's say we want 300 taxis or 500 taxis or however many. If you had the number that you were looking for on this side, and you had the 1.12 to the n, one way you could do it is graph it and look at where this side comes up, and you'd graph this side. It'd be a horizontal line, and you could find that value. That's lame. So how do we do that more efficiently? Well, we use logs. I'll show you this when we get back. But logs are a good thing because they help us calculate and solve for that exponent. They look scary, but basically they're undoing the function, right? If you were going to undo this 3x plus 2 function, you would have to make this the inverse of that, and so you'd have to undo 3x plus 2. And so to undo an exponential function, you'd use a log, right? And a log looks like this. Right? 2 to the x, if you looked at the exponential curve, it looks like this. Log curve is the inverse. It's reflected over the xy, and so you can tell that it has it's the inverse of this one because it follows that property. We're going to look at logs a little later, so let's just get to the fun stuff. This is the equation that we're used to seeing for exponentials. Base b to some power gives us a value a. You can switch this to log format for use in your calculator, which I'll show you later, or other interesting equations. And this is log. The base b is there, right? It's the little subscript. It tells you how many of the things you're multiplying together. A is the result, and x is the exponent. So, for example, if you have a whole bunch of 2's, you're multiplying them together. I know I want a bunch of 2's, I'm not sure how many, but eventually I want to get to 64. As a exponent, you could say 2, I've got a bunch of them, I don't know how many, but I want to get to 64. You could do this in your head, right? And say, all right, well, 2, 4, 6, 2, 4, 8, 16, 32, 64. So x should be 6, I think, right? Great, that's fine. And if you switch this into log format, you'd say, all right, well, this is log base 2, right? It means because 2 is the base of my exponents, that's what I'm using to multiply together. I want to get to 64. How many do I need, right? And you can throw this in your calculator, and it should spit out 6. Right? And I'll show you how to do that. Well, let's show you how to do that now. In your math key, right? In your math key right here, right? If you go down, you're going to have to go down almost to the bottom. It says log base, and you put the base in there. So put your 2 in there. Put 64 in here, and you should get out 6. 2, 4, 8, 16, 32, yeah, 6. Cool, try that. kiss that beauty. Right? This is nice for when you're not counting, right? If you have log base 2, what if we had not 64 but 70, right? Well, I know it's going to be, I'm going to have to multiply by some 2's. It's going to be bigger than this, but it's not going to be, it's not 128. If we multiply by 2 again, it's not, that would be 128. So log base 2 is 70 is going to be a decimal just a little bit bigger than 6.1 or something like that. Try it out. Cool. So I want you to be able to go back and forth today between exponential form and log form. So this 25 to the 1/2 is 5. If you wrote it in log form, it would look like log base 25. I want to get 5. 1/2 is my exponent. Same thing here. Base 10, exponent of 4, exponent of 4. That's the sum we want, the result we want. There's the result we want. So pause me and try to figure out this piece, that piece, that piece, that piece, and that piece. Yeah? All right, so this, we had base 6. Here's the exponent of -1, and 1/6 is our result. So we're just changing it back and forth. This is going to be log base A. I want C as my result, and B as the exponent. Logs solve the for the exponent. So the equals on the other side is always the exponent. Same thing here. I've got base 9. 2 is my exponent. 81 is what I want to get. Same thing here and there. Cool? All right, so that's it. I'd like you to try this piece in your outline, this graph of log functions. We're going to skip that. We're just going to do 2 and 3 so far. So skip this piece. You could try this, right? Evaluating, run those through your calculators. Make sure you can drive your calculator. And then move on to this part, log base A. You're just switching them back and forth. Some of you are already done with that. Keep moving on, keep moving on. You could try law of logs. The notes are up on the VLE. You can check out those if you're not sure, but carry on without me. I'm sorry I'm not there with you guys, but I'll see you soon. Bye.